The Fibonacci sequence is defined by each number being the sum of the two preceding ones. The first two terms are 0 and 1. The next term is 0 plus 1 equals 1, then 1 plus 1 equals 2, and so on. This process continues to generate the sequence. The Fibonacci sequence has many formulas for different uses, but here we focus on one simple representation for convenience in calculation. The Fibonacci sequence can be computed using recursion by defining the first two terms, fib 0 as 0 and fib 1 as 1. These return directly, while other terms are calculated as the sum of the two previous ones. For small n, like 30, it works quickly, but for larger n, like 60, it slows down significantly. Why? Each calculation splits into a tree of recursive calls, causing repeated work. For example, fib of 5 requires 14 calls. This inefficiency results in exponential time complexity, O of fib of n. To fix this, we use dynamic programming. Instead of recomputing, we store results iteratively. Starting with fib of 0 as 0 and fib of 1 as 1, each new term is calculated by summing the last two. For fib of 5, we need only 4 steps. This method has a linear time complexity of On, making it far more efficient. From the second method, technically, we have used the equation equivalent to a linear function calculating the matrix of f of n minus 1 f of n by f of n minus 2 f of n minus 1. After some transformation, we can show the multiplying matrix of this function. Continuing to use the formula for f of n minus 2 f of n minus 1. And since matrix multiplication is associative, we can multiply the multiplying matrices together to attain the new equality. Applying this process until we reach f of 0, f of 1, we attain the final equation to calculate the matrix, f of n minus 1 f of n. Thus, we have finished proving the formula for the third method of calculating the nth Fibonacci number using matrix multiplication. Now, let's compute the number of calculations if we use this formula of the third method. Firstly, matrix multiplication. To multiply two matrices together, we need roughly 8 multiplications and 4 additions. Secondly, matrix exponentiation. We have to compute the power of n minus 1, which would take n minus 2 matrix multiplications. Finally, we multiply the matrix, 0, 1, with the resulting matrix, which takes 4 number multiplications and 2 number additions. This means the new method here involves significantly more steps than the second method. So why do we still mention this approach? To answer, first, we shall learn a little bit about how to present a number in the binary system. Take the number 69 as an example. That means, in the decimal system, it is 69. In the binary system, this number is represented as 1000101. Here's why. In the decimal system, 69 is represented as where the number 10 is the base of the system, and the free factors are always less than 10. Now, in the binary system, the representation means a sum of powers of 2. Computing this sum, we obtain 69, which finishes our proof. When converting numbers from decimal to binary, we represent it by sums of powers of 2 and plug in values accordingly. In contrast, we can also convert a number from binary to decimal by writing it into a sum of powers of 2 and calculating that sum. The fast exponentiation method is a technique built upon the binary representation of numbers to calculate powers more efficiently. For example, you want to calculate the number 3 to the power of 69 using the traditional method. Normally, you would multiply 3 by itself 68 times, which means performing 68 steps. But is this the only way? The answer is no. There are far more effective ways to deal with the problem, one of which is applying the fast exponentiation method. First, You convert 69 into its binary form. In decimal, it translates to the shown expression. Taking the power of 3 to both sides, we derive the expression. There are several approaches to tackle this. For example, the ordinal method involves calculating x equals 2 to the power of I and then 3 to the power of x. However, using a recurrence relation as 3 to the power of 2 to the power of n minus 1 squared would be better in terms of operational efficiency. Hence, we shall calculate 3 to the power of 2 to the power of 0, then up to 3 to the power of 2 to the power of 6, then multiply those with powers of 1 together. Now we shall code it out. First, we set base equals 3 and exponent equals 69. Here's the for loop based on the calculation idea. We start the loop from the rightmost bit of the binary representation 100101, which is 1. Initially, current val equals the base 3 to the power of 2 to the power of 0. Since the bit is 1, we update result by multiplying it with current val. Then we square current val to calculate 3 squared to the power of 1. In the next iteration, the bit is 0, so the result remains unchanged, and we update current val to 3 squared squared. This process repeats for all bits, where we update the result only if the bit is 1, and continue squaring current val for the next power of 2. After 6 iterations, the result variable holds the final value of 3 to the power of 69. For computational complexity, the for loop iterates 7 times. Thus, for a general n, this result in a complexity of O log n. We come to the fourth method, to quick power version of matrix multiplication. We shall use the matrix formula achieved previously. From the equation, we see that computing the nth Fibonacci number is equivalent to calculating the nth power of the matrix, where we can apply the fast exponentiation method. The process is quite the same as calculating 3 to the power of 69. We shall start coding. First, take a look back at the code to calculate 3 to the power of 69. Now, we recreate the same function with some changes. We can see here that we set the current value equal to m. The result is the identity matrix. We set the binary exp as the binary form of the exponent. Afterward, we use the for loop. Here, we update the variable result and repeatedly square the current value using the matrix mul function. This function will be defined as a function that returns a matrix, which is the result of matrix multiplication. Finally, we define the function to calculate the nth Fibonacci number, using the equation mentioned previously. It's quite easy when all things are set. Just define a function and set a variable named m as the matrix. Calculate the nth power of it and save it into a new variable named m exponent. The result is the first element of the matrix that is the product of m and m exponent. About the computational complexity, recall that we have calculated the nth power of a matrix using the fast exponentiation method. So, should it be log 2 of n as mentioned in the previous part? But remember, instead of multiplying 2 integers together, we multiplied 2 matrices of size 2 by 2, each costing 8 multiplications and 4 additions. Thus, calculating the power of the matrix costs log 2 of n times 2 times 8 multiplications and log 2 of n times 2 times 4 additions. Thus, the complexity is O log n. To conclude, this marks our team's final effort in optimizing this code to the best of our limited abilities. Thank you for sticking with us.